A very good day to my supervisor Ms. JJ, dear Marcus, and my peers. Today I will be presenting my research project on thermal characterization and kinetic studies of empty fruit bunches derived lignin via green solvent extraction approach and its application in integrated biorefinery. An important aspect we look in the world today when it comes to engineering is sustainability. Hence today we identify greener ways of meeting our energy demands. So let me give a clearer background on this. As of the year 2020, fossil fuels still provide for over 70% of the world's energy demands. Because of that, migrating into renewable forms of fuels overnight would not be possible. This is why it is important to dive deeper into research in renewables. My research project observes one such measure. As you may know, the palm oil industry in Malaysia is significantly prominent and it is the second largest producer of palm oil, accounting for over 34% of the exports. The potential for OPEFB biomass as a source of renewable fuel have been growing rapidly, with more research being released. So you might be wondering what exactly OPEFB is and why is it feasible to be used as a source of biomass. Let me tell you a bit more about it. After the production of palm oil, it produces a waste material known as oil palm empty fruit bunches, or OPEFB for short. This OPEFB accounts for about 20% of the byproducts in palm oil production. OPEFB can be used in many applications, but only after following through some form of pretreatment. Moreover, the OPEFB produced is generally disposed, which actually contributes negatively to the environment and also proves to be a significant cost to the crude palm oil manufacturer. In Malaysia, an annual 21 million tons is disposed, which would be otherwise well used as a source of fuel, allowing to recover as much energy as possible while minimizing the waste disposal. So my research project aims to review the various literature and identify potential effect of LTTM pretreatment methods for OPEFB, and moreover determine the effect of LTTM pretreatment on the thermal degradation behavior of biomass using thermogravimetric analysis, and lastly to identify the potential kinetic model for the thermal degradation behavior of LTTM treated OPEFB. And this gives rise to a series of research questions. Firstly, how does the LTTM pretreatment modify the physiochemical properties of OPEFB? And then, what are the thermal degradation behavior of OPEFB before and then after LTTM pretreatment? And lastly, which kinetic model can best predict the thermal degradation behavior of LTTM pretreated OPEFB? Moving on to the literature review, the transformation of biomass such as OPEFB used in this poster can be used as a renewable source of fuel, which is generally followed by several stages of research and processing. In general, out of these stages, an important part of the process is pretreatment. So generally, the process of pretreatment can be done either physically, chemically, or as a combination of both to open or stretch the lignocellulosic structure. So there are four pretreatment methods that are shown in this poster, which is option A, alkali pretreatment, that is followed with sodium hydroxide or ammonia, and then option B, which is the dilute acidic pretreatment, which can be used with either formic acid or acetic acid, and lastly option C, which is organosolved delignification, which uses ethanol and sulfuric acid as the catalyst, and option D, which is LTTM or low transition temperature mixtures using malic acid and sucrose. So as I addressed before, sustainability is important, and hence the development of ideal green solvents with high sustainability which are safer for both humans and environment is critical. As all other pretreatment methods show a poor biocompatibility, this is where LTTM comes in. It's a new generation of designer solvents that could be ideal for the separation of main biopolymers in lignocellulosic biomass such as lignin, cellulose, and hemicellulose. And LTTM can be synthesized with a hydrogen bond acceptor and a hydrogen bond donor. So malic acid here acts as the hydrogen bond donor, whereas sucrose acts as the hydrogen bond acceptor. In order to model this degradation behavior, we will be following the distributed activation energy model. The DA model can be used in an isoconversional approach to portray the biomass decomposition behavior, and the decomposition behavior of OVEFB can be said to occur in a set of first-order irreversible reactions. So there are several distribution functions that the DA model can be used with. But after investigating through multiple literature resources, it was evident that one of the most successful when comparing with experimental data was the Gaussian distribution function. The methodology on this research project is categorized into three main steps. The data from the TGA of LTTM treated OPEFP is taken from a postgraduate student in order to carry out the modeling. So to develop a suitable model, the parameters that is involved, including the Arrhenius constants and activation energy, needs to be identified for the experimental data. And then, using a suitable algorithm, a model equation is derived after retrieving the unknown parameters. Once a suitable model is obtained, it can be tested and evaluated in the model validation stage to identify if it is capable of successfully portraying the behavior that is expected out of the LTTM pre-treated OPEFB. So for my future work in FYRP2, it would involve the identification of a suitable MATLAB algorithm which is capable of running multiple iterations on different data points, and thereafter the model can be discussed on its fit on the degradation behavior in order to evaluate how well the distributed activation energy model can depict the thermal degradation behavior of LTTM treated OPEFB. So lastly, I would like to extend my gratitude to my supervisor, Ms. JJ, for guiding me throughout this project. And for the references of this project, there will be a QR code on the poster, which you can scan to go through more information and articles regarding this. Thank you for your time, and if you have any questions, please feel free to drop them on the discussion forum. Thank you.